filmed using a high-speed camera.
Launch in 3, 2, 1, go!
This footage of the model train exiting the pipe was taken with a high-speed camera. Just before it emerges, the confetti at the pipe exit is sent flying. Then, after that, the train itself emerges. This is how a static pressure wave occurs. It is a wave of air that exits the tunnel ahead of the train. This footage shows the change in air pressure as a train enters a tunnel. Red areas indicate higher pressures. As the train enters the tunnel, the red zone expands as pressure rises. The red zone advances through the tunnel faster than the train itself. This is the static pressure wave, which causes vibration and noise at the tunnel exit. In general, the faster the pressure wave travels, the more energy it contains. So on lines such as the Tohoku Shinkansen, where there are many tunnels, increasing train speed is a matter of concern. How can the static pressure wave be reduced? A special environmental impact mitigation team was formed to investigate. Takeshi Kurita is one of the team's members. Kurita and his team focused on the shape of the train's nose. It is an established fact that the longer and more slender the nose, the less the pressure change and the smaller the static pressure wave. So the nose of the Fastek was extended to 16 meters, longer than any other train in the world. In addition, 2 different nose shapes are being tried out. The arrow line nose is rounded. The streamline nose is pointed. The 2 shapes made test runs through tunnels to measure the size of their pressure waves.
When the test results are analyzed and expressed in terms of numbers, the arrow line shape produces a 10% smaller static pressure wave than the streamline. So this is the one with the smaller pressure wave. We did several experiments, and in all of them the arrow line performed better in every way. There is a significant difference between the 2 nose shapes.
This shows the pressure change difference between the 2 shapes. Red indicates higher pressures. Comparing the 2, the rounded arrow line shape displays a wider spacing between the lines indicating pressure, showing that the rise is more gradual. This is thought to hinder or at least retard the formation of the static pressure wave.
The arrow line shape does not come to a sharp point. It's deliberately made more rounded. When we study the airflow around it, we can see that the airflow is stalled around the rounded parts, and that is quite clear. Around here is where the air begins to flow. The longer the nose, in this case it's 16 meters, the greater the area of stalled air, which has the same effect as having a pointed shape.
The front of the train isn't just designed to achieve more speed, it also takes environmental impacts into account. That's ingenious, isn't it?
Yes. Well, the point is, these static pressure waves produce a sudden boom, even when no train is visible, and the sound reverberates through the mountainous areas where tunnels are most common. Well, that's an undesirable effect, which needs to be mitigated if possible. But the fact is, higher speeds contribute to static pressure waves, so the need to modify those waves influences the design of the lead cars of trains designed to run at high speed.
So why are these static pressure waves more of a problem in Japan than in Europe?
Well, because of much flatter land. French bullet trains run on lines with hardly any tunnels. So it all depends on where your high-speed train network is going to be built. There are now plans to extend the French high-speed rail network to the Alps and hilly parts of the Mediterranean area, where tunnels will be required. When that happens, French engineers will not be able to avoid dealing with this problem.